I know this will disappoint you, but we're going to hold off on that extended discussion of the TCP three-way handshake for just a little while because it's time for us to get to some lab work. I know this section's been heavy on theory so far. We got to do a little bit more here with the Cisco IOS zone-based firewall, go over some fundamental rules. And then we've got a couple of great labs for you, I think over an hour of basic firewall and advanced firewall configuration on another GUI called the Cisco Configuration Professional. We will be going back to the ASDM later in the course, but you need to see CCP as well. They're an awful lot alike, so no huge learning curve there. And if you've taken this security course with me before, the labs will look familiar because they're so good. I want you to see these. So we're running those again with the basic and advanced firewall wizards. But first, there are a few rules we need to know about this entire zone-based firewall deal. And of course, the first question is, what exactly is a zone? Well, with Cisco zone-based firewalling, ZBF, zones are simply logical groups of interfaces. That's all there is to it. A couple of immediate and important points that will save you heartbreak and exam points. First off, a zone does not necessarily contain every interface on a router. It can. Certainly, if it's an internal router, you could have all the interfaces in your inside zone, but it's not a rule. Now, an interface can belong to only one zone, a rule that I will probably mention more than once in the next 15 minutes or so. But again, a zone does not necessarily contain every interface on a router, and an interface can belong to only one zone. We're going to wash those down with two vital defaults. First off, traffic will flow freely between interfaces in the same zone. Of course, everything else being equal as long as they can reach each other, that kind of thing, via the routing table. And traffic does not flow at all between interfaces in different zones. So you're thinking, that could be a little bit of a problem. So here I've got zone A and zone B. Ordinarily would say inside zone, outside zone. Just felt like being a little different. But the concept remains the same. In this particular illustration, interfaces 1, 2, and 3 can exchange traffic, no problem there. Interfaces 4 and 5 could because both interfaces on that router are in the same zone. But by default, traffic could not flow between interfaces 3 and 4. And you know the magic phrase, by default. That means there's got to be some way we can do it. Because otherwise, if we put this in our network's going to come to a crashing halt if all of a sudden we have interfaces that could exchange traffic previously, but now cannot. But before we get to that, we got one other little zone to look at here. And it's like with ACLs, when you have traffic generated on the local router and you want to match an ACL against it, you have to take some different steps. Well, the same goes here with firewalling with ZBF, because traffic generated on the local router, that's where the self zone comes in. And this zone covers traffic destined for an IP address that is present on the local router, which is entering the self zone, and traffic generated by the router and leaving, and as you would expect, that is called exiting the self zone. Sounds very zen there. All of this traffic is permitted by default. So if we're looking at this particular router, 10.1.0.0.16 on the left, 10.2.0.0.16 on the right, if traffic is coming into that router and its destination is 10.1.1.1, well, that's an IP address on the local interface, on the local router, and that is considered to be destined for the self zone. Traffic leaving, in this case, 10.2.1.1, it's got that source address. That's locally generated traffic flow, and that again would belong to the self zone. Now let's talk about some zone pairs. We now know that interzone traffic is not allowed by default, but as we could see very quickly, it's a rare network indeed where we are not going to need some kind of interzone traffic to be permitted. Otherwise, again, our network's going to come to a crashing halt. We can do just that with a little something called a zone pair. It's a unidirectional set of rules that will be applied to interzone traffic. And if you're like me, maybe this is the first time you're seeing this and you're thinking, okay, zone pair, it's a unidirectional set of rules. If I asked you to hand me a pair of shoes and you just handed me one shoe, I would say, well, where's the other one? But the thing with zone pairs is they're unidirectional. The zone pair only points one way. We're not talking about a pair of permissions, so to speak. It's that zone pair that allows one to talk to the other. And the zone pair only points one way. So if you want a host to initiate a data flow to a server and the server to be able to initiate a data flow to the host, we need two zone pairs. Let me show you the illustration that goes with this. It'll be a lot more clear. And you can see that we have a host on the left side in what we call our inside zone. We have Cisco iOS Firewall, which is a router running zone-based firewalling, but this is a symbol that I found that we like to use. It's got the firewall and the iOS in there. And it's connected to an outside zone, and there's a server out there. Well, again, if we want the host to be able to initiate conversations to the server and the server to be able to initiate communications back, we would actually need two zone pairs, one inside to outside and one outside to inside. Now, we can allow that interzone traffic via zone pairs by permission or inspection. And there's a huge difference between the two. The big similarity is that both actions allow interzone traffic, but the overall effect is different. And what we're going to do is do a walkthrough from the host point of view and with only one zone pair in place. So this is what we're looking at right now. Again, we've got our host in the inside zone, a server in the outside zone, but the only zone pair that we've configured right now is inside to outside. Well, with permit, the host could send traffic to the server if we did a permit here, but the server can't reply. Why not? Because there's no entry made in the state table. We are permitting traffic only. So in this particular case, host could talk to server, but server could not reply because that reply traffic would come back. The iOS firewall would look at it and say, hey, I got nothing in my state table for this guy. It could be dangerous traffic, so I'm getting rid of it. There's no outside to inside zone pair. But there is an instance where you don't need an outside to inside zone pair here, and that is when you go with the inspect rule on your zone pair instead of permit. Because with inspect, that would allow the host to send traffic to the server, but while the traffic is going through, an entry is made in the iOS firewall state table. So in this particular case, the server could reply to the host even if no specific zone pair allows it. Because again, inspect puts an entry in that state table, the traffic comes back from the server, it hits the iOS firewall, it looks in its state table and says, okay, I got an entry for you, I'm going to let that traffic go on in. So again, permit, let's go over these, a very important distinction here. Permit, the host could send traffic to the server, no entries made in the state table, so a reply would not be possible unless we had another zone pair in place allowing that particular server to talk to that particular host. With inspect, since the packet is inspected and an entry is made in the state table, a reply is possible without a zone pair going outside to inside. Now, let's see, we've got a little something called the DMZ here because I want to show you this particular drawing first. I know that the term small network or simple network, you know, it's all relative, right? If you're in charge of it, it may not be all that simple. But if you have a situation like this, where you've just got a couple of servers on the inside, you've got a couple of hosts on the inside, obviously more than I've illustrated here, but you know, just some servers, just some hosts that need to talk to each other and they all need internet access, then you know, this configuration would be fine. You know, you could just go with an inside zone with all of our internal network devices, then you just go with one giant outside zone, which is basically, you know, everything outside your network. And of course, that way would be internet access as well. But what if you had servers that needed to be accessed by the public? Let's say that this network had some money servers, some e-commerce servers, the ones with little money bags next to them. If you've never seen them before, you'll see them in a minute. Well, the thing is, e-commerce servers or even web servers, you know, that wouldn't do us much good in our internal network if external hosts could not access them. You know, if external hosts cannot access our e-commerce servers, we're not making very much money. So what we might need then is something a little more complex, because what we wouldn't want to do, unless we absolutely had to, was put those e-commerce servers in our inside zone. Because then to allow outside users to access our e-commerce servers and our web servers, we'd have to let them into our internal network, and we really don't want that. That's where the DMZ comes in, officially standing for Demilitarized Zone. It's a military term, as you would expect. It's really an area where warring factions agree that, hey, we're not going to fight here. You know, it's a demilitarized zone. Well, we're not going to have physical bullets flying around in our network, but we do want some protection logically for those e-commerce servers and web servers I mentioned a moment ago, and that's where the DMZ comes in handy. We're going to talk about that feature in the very next video, and I'll see you there.